My name is Robert Decoursey. I work at NASA Langley Research Center, and I supported Ares 1X project as the software mission assurance manager, and overseeing all of the flight and ground software, mostly related to avionics. The risk was Atlas heritage software controlling non-Atlas hardware, and the issue would be something going wrong with the control of the hardware. So the software maybe not driving the hardware quite the way it was expected. And so there were 3 shuttle-derived avionics boxes on Ares 1X that Atlas software was required to control, and there was 1 new box, the Ascent Thrust Vector Control Unit, that was built by Honeywell and specifically for this mission that the Atlas software had to control. Those are, as I mentioned, boxes that were not tested previously with Atlas software, and which led to a lot of additional testing for Ares 1X. In addition to a successful Atlas program, Lockheed's software and hardware were also chosen because of the thought that a heritage system like that would be cost-effective and schedule-effective. We had a very short schedule to get Ares 1X off the ground, and Lockheed came with a set of avionics in-house, a set of software in-house, and a lot of test experience. So those are the reasons that Lockheed was chosen. There's always a risk of something unknown coming up later on with respect to the software and the hardware that you're buying as you integrate that with the vehicle, and you come to find out that maybe the system wasn't designed for this 30-year-old hardware that's coming off of the shuttle, and problems come up, and a lot of those are found, as we'll get to in testing. Here at NASA, the strategy of test like you fly and fly like you test has been adopted and adhered to for a long time. And during the development of Ares 1X, it turned out that we had 20 to 30,000 different parameters that had to be tested. All of them had to be tested, and all of them had to be tested in a flight-like configuration. So simulations that were run had to be flight-like. To mitigate the risk of a failure, we had a test plan originally drawn up by the contractor and reviewed by several independent groups, including NASA, Aerospace Corporation. We actually had a company called Analyx look at it as well. And with the thought of, or with the intent of looking at the test plan to determine whether or not it was a suitable test plan for a first flight vehicle like this. So we had many different groups, as I just mentioned, look at it and come back with comments and updates to the test plan and additional tests that, for instance, the GNC group here at Langley looked at the test plan and decided there were several tests that were not captured or were not adequate. So those comments were incorporated. It was an iterative process. So we being NASA Langley, NASA Marshall Space Flight Center, Avionics Group looking at the test plan, and then these other companies like Aerospace and Analyx looking at it, supplied comments to the contractor Lockheed, and the test plan was updated, returned back to NASA for approval, and then it was not executed until everyone had signed off on the test plan. During the analysis of the test plan, we were looking and thinking about the past successes and failures of other programs, including issues with parameters, including issues with avionics, and maybe issues with software that was what some people call dead code or unreachable code that isn't expected to execute on a particular flight. And how you would go about testing and verifying that those things were going to operate as you would expect, as you would hope. Software testing was performed for the most part on a system called FASTER, which stands for Flight Analogous Software Test Enhanced Resource. And it is a system that is built specifically for flight code testing. And in it, you have the ability to simulate a bunch of different environmental effects like high winds, low winds. And you can basically run through a set of tests in a very short amount of time. The Ares 1X flight was expected to be about 2 to 3 minutes. So running through a test on the faster system, you can run through it in 2 to 3 minutes. It takes a few minutes to get to the countdown point to T0 and then 2 to 3 minutes to fly the mission. But what that means is on a system like Faster, you can run a complete test in 5 minutes, set up the system again with some configuration files, and run another test. So you can run through several of these scenarios in 1 hour. And since the Ares 1X flight software test plan was approximately 60 tests long, it allowed the test engineers to get through the entire test plan within a matter of just a few weeks, and to redo any tests, rerun any tests that didn't go the way they expected or thought they needed to be tweaked in some way, added, some new perturbation added to the test. Sometimes we actually had things that were supposed to break in a test, and they didn't break the way we expected them to because something wasn't configured correctly or something didn't operate quite the way we thought. And so the test had to be rerun. And so you can get through a lot of these tests very quickly with that sort of setup. So flight software was tested in this Faster system. But for integrated test, in order to test the hardware working with the software, you needed another system, and in this case it was called the SIL, System Integration Lab. And that is a combination of avionics ground software, flight software, and all the avionics boxes, including the flight computer, all of the rate sensors, and the shuttle-derived avionics that we mentioned, and the thrust vector control unit box. That was a new box built by Honeywell. The SIL allows you to run through. It takes a while to run through a test in the SIL. It's a lot longer process to get the hardware configured, to get everything in place. But you can run through several tests in a day in the SIL, and it allows you to test things like battery failure. Batteries are simulated in the SIL, but it's still, you can take a simulator and pull. We have two main batteries on Ares 1X. You can pull one off in the SIL and make sure that the system still functions correctly. You can do certain things to the shuttle boxes to make them appear as though they were broken, a connection was lost, something like that, and show that the redundancy in the system still works. So those sorts of things in the SIL, there were about 13 to 14 specific tests in the SIL that were run to verify that the flight software and the flight avionics were going to operate together as a team. The final test for this was run in the VAB, the Vehicle Assembly Building, and the test was called the Launch Vehicle Readiness Test. And that test allows you to do the same, very similar things what you do it in SIL, but it allows you to do things on the rocket after the vehicle is completely integrated. All the wire is in there. Everything is connected. It allows you to move the nozzle at the base of the rocket using hydraulics from Kennedy Space Center, and go through and check out all of the pyro connections without pyros being in place, but in order to verify that the connection is there. At the end of launch vehicle readiness test in the VAB, we had confidence that the Lockheed avionics and Lockheed software could drive the shuttle-derived avionics and the new box, the Ascent Thrust Vector Control Unit. The three, as I haven't mentioned them previously, but the three shuttle-derived avionics were the ignition separation controller, the recovery control unit, and the APU controller. But as I said, following the LVRT test in the VAB, there was sufficient evidence through all of the SIL testing, the Faster testing, and then this LVRT to close out the risk and to move forward on to IST, or integrated system test at the pad and launch. Coming out of the, as I mentioned earlier, I came out of the Safety and Mission Assurance Office here at Langley, and was responsible for safety and software mission assurance on the project, which includes software assurance, reliability, and software safety. And The assurance portion of the job was basically making sure that the contractors who were doing the bulk of the development followed their process that had already been approved, as the contract was let. The reliability is a factor of making sure that there is redundancy in the system and that the tests are adequate. And as we've already covered, we've gone through the faster SIL LVRT testing that took place. And then safety, Constellation Project, our program, instituted a system called CSERP, or Constellation Safety Engineering Review Panel, that requires that each project develop their own hazards for every software component that could either cause a problem or control a problem, a hazard, and bring those hazard reports to CSERP, this engineering review panel. And so Ares 1X went through the CSERP process. We wrote up all the hazard reports, went to CSERP 1, 2, and 3, where you lay out your hazards for this board in the first phase, and then CSERP phase 2, you come back with controls for the hazards, and then CSERP phase 3, you show that you have verification for those controls in place, and that you show that you can close those hazard items by closing off the verifications that you've listed. So you've got to basically, and by CSERP phase 3, you have to have a complete hazard report with controls and verifications and a plan to close those verifications. So every couple of days we'll have an SRB to discuss requirements issues or a test plan issue. And towards the end, all we're doing is testing. And so a lot of times you'd have an SRB to discuss a test plan problem. They would run through a test in FASTER or in SIL, and they would find that the test didn't go the way they had hoped. Something didn't break when it was supposed to break. Something did break, and they didn't expect it to. And so these SRBs would take place as needed to make sure that things moved along quickly. And NASA and Lockheed and Aerospace were all on these phone calls generally to make sure that the process moved along smoothly. And this communication process really did help out. And one of the main things where this communication really helped out was with those parameters that we discussed earlier. Of those 20 to 30,000 parameters, NASA was responsible for about 10 to 15,000 of those parameters. The way that parameter process took place was this communication that we had every week or every few days, where NASA supplied those parameters in a formal formatted form, generated in a spreadsheet, supplied to the contractor. The contractor would ingest those parameters, feed them into their software, pull them out of the software, send them back to NASA, and make sure that nothing got garbled, everything was as it was expected. So that process of making sure that the parameters got generated here properly, got ingested into the software at Lockheed properly, spit out and returned to Langley, and verified, was a process that we did find errors on occasion, and that process actually made reduced schedule risk. We were able to move along faster because communication was on an almost daily basis. So one of the lessons learned on the project, and specifically relative to this risk of heritage software and non-heritage hardware, is a good relationship with the prime developer helps out in either mitigating risks and mitigating all risks, including schedule risks. And in this case, NASA had a very good relationship with the prime contractor. We met on a weekly basis with a group called Flight Dynamics Working Group that was led by a man here named Jay Brandon with the Lockheed people. Every week they would talk about flight dynamic issues, any sort of problems with the requirements documentation, any problems with testing that was going on. And then in addition to that weekly call, we also had almost daily calls in the last 6 months of the project. We had daily or every other day phone calls called SRBs software review boards with the contractor to discuss any changes in requirements in any of the flight software or the ground software, any issues that came up in testing related to any of the components that were flying. The importance of testing as you fly and fly as you test was evident as we integrated the vehicle at Kennedy and noticed that we were having issues with the DFI, the development flight instrumentation. There were issues with cabling. Some of it was pretty simple, like something was labeled incorrectly, something a little more of an issue, like a cable end that was pinned incorrectly. And those sorts of things were not tested in the SIL. There were 700 to 800 DFI sensors on the vehicle, and it was going to be impossible to get 700 to 800 sensors integrated into the SIL. But because we could not do the integration in the SIL and do all of the testing in the SIL for DFI as we had for the rest of the vehicle, the bulk of the issues that came up during integration at Kennedy were related to DFI. And I think that really does say something about how important it is to test what you're going to be flying. So the lesson for me with respect to DFI and with respect to the entire vehicle is to test as you fly. As I mentioned there, the DFI system wasn't fully integrated in the SIL, and that accounted for many of the problems that we saw during integration.